Hi lovely people, welcome to my channel. If you are interested in speaker design and improving sound quality, subscribe and join us.
In the first part, we spoke a bit about common specifications of horns. Today, we're gonna focus on some types of horns. The first tip to calculate and design the horns is the wave equation. Even scientists may be exhausted with this method. Today, we're going to design horns with the help of very simple formulas in Excel and an acoustic simulator. Exponential horns. This horn first was evaluated in the 20s by the American Institute of Electrical Engineers. In most horns, the first step is to define a cutoff frequency. Cutoff means below this frequency, the horn transmits nothing. The higher the cutoff frequency, the shorter the horn, and the less the frequency range taken from the speaker. Suppose the cutoff frequency is 75 Hz. 75 Hz is an example, and you can select your desired frequency and do all steps as well. From here on, we get into a bit of horns math, which is pretty simple. If you like the video so far, like and share the video. In the formula of exponential horn, F is the cutoff frequency. M is the flaring factor. C is the sound speed and is equal to 343 meters per second. As you can see, M equals 2.75 at this frequency. ST is the throat area or your driver area. S becomes bigger in every step. M is a fixed value and equals 2.75 for this design, and the only thing that will change is the distance from the throat, or X. It is very simple to implement this formula in Excel to get the side view of the horn. The side view is enough to design the horn in simulators and reality. EXP in Excel is the exponential function, and all the parts of this formula can be implemented. A very important thing to know that this formula is for an infinite horn. It means the frequency response for a short horn will be no longer linear, and it contains sharp peaks which destroys the sound quality. But we can terminate an infinite horn and get a good sound quality from short horns with the simple condition. If the numerical ratio of the circumference of the horn mouth to the wavelength at the cutoff frequency is higher than 1, we will have a qualified horn whose impedance fluctuations can be neglected. KRM is the ratio of the circumference of the horn mouth to the wavelength. As you know, the wavelength is the ratio of the sound speed to the frequency. The sound speed equals 343 meters per second, and the selected frequency was 75 Hz, so the result will be obtained to be 4.5 meters, and the circumference of the horn mouth must be greater than 4.5 meters to get a good result. The effect of KRM on increasing sound quality and eliminating the fluctuations is very noticeable. In these graphs, the KRM changes between 0.23 and 0.93, and the closer value to 1, which is 0.93, here, smooths the graph effectively. So this is one of the keys to getting a good horn. In the Excel file, the growing column illustrates S in every step. X column is displacement. With a very simple formula, you can obtain the circumference and the radius in every step. Everything is ready to obtain the KRM, and we need to find its value more than 1 to get a qualified horn. For a 75 Hz horn, the length will be obtained to be 2 meters, and the KRM equivalent to this length will be about 1.16. The radius will be 0.8 and the circumference 5.3 meters. Now, you can make your horn with this table, but we should simulate this in a software to get an accurate result of its impedance response. This is the radiation impedance formula. We don't need to write it in Excel. We simulate it in acoustic and get all the specs. You can watch this series of videos and practice to master it. In another video series, we simulated exponential horns from 0 to 100. Watch and do it step by step. The results help you to get a standard horn. It is not bad to mention the defects of this horn. As can be seen, the green area becomes narrower with increasing frequency. This means that if a person is not in front of the horn, he will not hear the high frequencies properly. Suppose we put a number of similar horns next to each other, which means these narrow patterns create a bigger area for the listener, and the sound pressure has a fixed level in a wide area. And the resulting horn will be a multicellular horn, which is a very useful method to improve the sound quality. It doesn't mean that a single horn is not usable. As I said, a single horn in high frequencies has a narrowing effect named beaming, and in mid-frequencies can be mounted on mid-ranges and woofers. Always use accurate software to design a horn. First, you can make horns with cardboard. After that, try to use wood or fiberglass. Then compare the results with the calculations of the software. The horns world is so beautiful, and many DIYers use them to remove the complexity of the other methods of directivity control. If you want me to make more videos about horns, write in the comments below.